Close your eyes for a moment and let your mind drift into the infinite expanse of the universe. Picture a canvas so vast, so unimaginably large, that every star, every galaxy, is but a tiny brushstroke on its surface. Now, imagine that this cosmic masterpiece is held together by something invisible, something we cannot see or touch, yet it shapes everything we know. This is the story of dark matter, the unseen force that weaves the fabric of the cosmos, guiding galaxies into existence and holding the universe in its delicate balance. Tonight, as you settle into the quiet of your space, let us take you on a journey through the stars, where mysteries unfold and the invisible becomes the foundation of all we see. Where are you joining us from, and what time is it there? As the night wraps around you, let the whispers of the universe carry you into a world where science meets wonder and the secrets of the cosmos await. Now, let us step deeper into the mystery of dark matter. Imagine standing in a room filled with invisible threads, threads you cannot see or touch, yet you feel their pull, their presence shaping everything around you. This is the essence of dark matter. Unlike the ordinary matter that makes up stars, planets, and even our own bodies, dark matter does not interact with light. It does not glow, reflect, or absorb it. It is entirely invisible to our eyes and our most advanced telescopes. Yet, its presence is undeniable. How do we know it exists? The answer lies in the way galaxies move and behave. When scientists observed galaxies spinning, they noticed something strange. The outer edges of these galaxies were moving far too quickly to be explained by the visible matter alone. There had to be something more, something unseen, exerting a gravitational pull strong enough to hold these galaxies together. This invisible force, this hidden scaffolding of the cosmos, is what we call dark matter. It is the silent architect of the universe, shaping galaxies and guiding their motion, all while remaining shrouded in mystery. And as we continue our journey, we will uncover more about how this unseen force shapes the very fabric of the cosmos. Now, let us turn back the pages of history to uncover how the mystery of dark matter first came to light. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a massive group of galaxies millions of light years away. He noticed something peculiar. The galaxies within the cluster were moving at speeds that defied explanation. Based on the visible matter alone, the cluster should have flown apart, yet it held together. Zwicky proposed the existence of what he called dunkel materie, or dark matter, an invisible substance providing the extra gravitational pull needed to keep the cluster intact. Though his ideas were groundbreaking, they were met with skepticism at the time. Decades later, in the 1970s, astronomer Vera Rubin and her colleague Kent Ford brought new evidence to the table. They were studying the rotation curves of spiral galaxies, mapping how stars moved at different distances from the galactic center. What they found was astonishing. Stars on the outer edges of galaxies were moving just as fast as those near the center, a phenomenon that could not be explained by the visible matter alone. Rubin's work provided strong support for Zwicky's earlier hypothesis, showing that galaxies were embedded in vast halos of unseen matter. Her discoveries revolutionized our understanding of the universe and brought dark matter into the scientific mainstream. These breakthroughs were not just isolated moments of insight, but part of a growing body of evidence. Over time, observations of galaxy clusters, gravitational lensing, and the cosmic microwave background, radiation, all pointed to the same conclusion. Dark matter is real, and it plays a crucial role in shaping the cosmos. The work of Zwicky and Rubin laid the foundation for a new era of astronomy, one where the invisible became as important as the visible. And as we continue to explore, we find that dark matter is not just a scientific curiosity, but a key to understanding the universe itself. With this foundation in place, let us now turn our attention to how dark matter interacts with the ordinary matter we can see, and why this invisible force is so essential to the structure of galaxies. Now, as we venture deeper into the cosmos, let's explore the fascinating contrast between dark matter and the ordinary matter that makes up everything we can see and touch. Ordinary matter, the stuff of stars, planets, and even our own bodies, interacts with light and other forces in ways we're familiar with. It reflects, absorbs, and emits light, allowing us to observe it directly through telescopes and other instruments. But dark matter is entirely different. It doesn't interact with light at all. It neither emits, absorbs, nor reflects it, making it completely invisible to our eyes and traditional detection methods. This is why we call it dark. It hides in plain sight, revealing itself only through its gravitational effects. The differences don't stop there. Ordinary matter is made up of particles like protons, neutrons, and electrons, which form atoms and molecules. These particles interact through electromagnetic forces, creating the complex structures we see around us. Dark matter, on the other hand, seems to interact only through gravity. It doesn't form atoms or molecules, and it doesn't clump together in the same way ordinary matter does. Instead, it forms vast, diffuse halos that envelop galaxies and galaxy clusters, providing the gravitational scaffolding that holds them together. This distinction is crucial for understanding the universe's structure. Without dark matter, galaxies wouldn't have enough mass to hold themselves together. The stars on the outer edges of galaxies, for example, would fly off into space due to their high speeds, but dark matter's gravitational pull keeps them in place, acting like an invisible glue that binds galaxies together. It's also responsible for the large-scale structure of the universe, shaping the cosmic web of filaments and voids that connect galaxies across vast distances. So, while ordinary matter builds the visible universe, stars, planets, and life itself, dark matter provides the unseen framework that makes it all possible. Together, they form a delicate balance, one that allows galaxies to form, evolve, and thrive. And as we continue to study this invisible force, we uncover more about the hidden architecture of the cosmos, reminding us that there's far more to the universe than meets the eye. With this understanding of how dark matter and ordinary matter differ, let's now turn our gaze to the cosmic web, the intricate network of dark matter filaments that weaves the universe together. Now, let's step into the grand tapestry of the cosmos, where dark matter weaves an intricate and invisible framework known as the cosmic web. Picture the universe not as a random scattering of galaxies, but as a vast, interconnected network, much like the threads of a spider's web stretching across unimaginable distances. This cosmic web is made up of dark matter filaments, long, thin strands of invisible material that crisscross the universe, connecting galaxies and galaxy clusters in a delicate yet powerful structure. Imagine these filaments as the backbone of the cosmos, the hidden scaffolding that holds everything together, just as the steel beams of a skyscraper provide the support needed for its towering height. Dark matter filaments give shape and stability to the universe. They act as cosmic highways, guiding the flow of gas and dust that eventually forms stars and galaxies. Without this web, the universe would lack the structure necessary for galaxies to form and evolve. The cosmic web isn't just a static framework, it's dynamic and ever-changing. Over billions of years, gravity pulls dark matter into these filaments, creating dense regions where galaxies cluster together. Between these filaments lie vast, empty voids, regions of space where matter is sparse and galaxies are few and far between. This interplay of dense filaments and empty voids creates the large-scale structure of the universe, a pattern that astronomers can map using advanced telescopes and simulations. To truly grasp the scale of the cosmic web, think of it as a three-dimensional network spanning the entire observable universe. Each filament can stretch for millions or even billions of light years, connecting clusters of galaxies like beads on a string. And just as a spider's web is stronger than it appears, the cosmic web's dark matter filaments exert a gravitational pull that shapes the destiny of galaxies, guiding their movements and interactions over cosmic time. This invisible architecture is what allows galaxies to form and grow. As gas and dust flow along the filaments, they accumulate in the densest regions, collapsing under gravity to ignite the birth of stars and galaxies. The cosmic web, in essence, is the universe's blueprint, a hidden design that dictates where galaxies will form and how they will evolve. As we marvel at the beauty of galaxies scattered across the night sky, it's humbling to remember that they are all connected by this vast, invisible network. The cosmic web reminds us that the universe is not a chaotic expanse, but an organized, interconnected system, shaped by the unseen hand of dark matter. And as we continue to explore this hidden structure, we uncover more about the forces that bind the cosmos together, revealing the intricate dance of matter and gravity that has shaped everything we see and everything we cannot. With this understanding of the cosmic web, let's now turn our attention to the basics of galaxy formation, where dark matter plays yet another crucial role in shaping the universe as we know it. Now, let's take a closer look at how galaxies come into existence, a process that begins with the simplest of ingredients, gas and dust, and the invisible force that binds them together, gravity. Picture the early universe as a vast, swirling sea of particles, where tiny ripples in the fabric of space and time began to grow, thanks to the relentless pull of gravity. These ripples, amplified over billions of years, became the seeds of galaxies. At the heart of galaxy formation lies gravity, the cosmic architect that shapes the universe. Gravity works like a cosmic magnet, drawing gas and dust particles toward one another, Over time, these particles clump together, forming denser and denser regions. As these clumps grow, they begin to collapse under their own weight, heating up and igniting the first stars. But gravity doesn't work alone. It has a silent partner, dark matter, which plays a pivotal role in this process. Dark matter, though invisible, provides the gravitational scaffolding that allows galaxies to form. Imagine dark matter as the framework of a house, while gas and dust are the bricks and mortar. Without the framework, the structure would collapse. Similarly, without dark matter's gravitational pull, gas and dust would simply drift apart, unable to coalesce into galaxies. Dark matter's presence creates the gravitational wells that trap ordinary matter, guiding it into the dense regions where galaxies are born. As these regions grow denser, the gas within them begins to cool and condense, forming clouds that eventually collapse to create stars. These stars, in turn, gather into clusters, and over time, these clusters merge to form galaxies. The process is slow and gradual, taking billions of years, but it's this intricate dance between gravity, dark matter, and ordinary matter that gives rise to the galaxies we see today. What's fascinating is that dark matter doesn't just help galaxies form, it also shapes their structure. The distribution of dark matter determines how galaxies are arranged in space, influencing their size, shape, and even their movement. For example, spiral galaxies, with their elegant arms of stars and gas, owe their structure in part to the dark matter halos that surround them. These halos act like invisible cocoons, holding galaxies together and guiding their evolution. As we explore the basics of galaxy formation, it's clear that dark matter is not just a passive observer, it's an active participant, shaping the universe at every turn. From the first clumps of gas and dust to the majestic galaxies we see today, dark matter's influence is woven into the very fabric of the cosmos. And as we continue to study this mysterious substance, we uncover more about the forces that have shaped our universe, revealing the delicate balance between the seen and the unseen. With this foundation in place, let's now delve deeper into the concept of dark matter halos, the invisible structures that surround galaxies and play a crucial role in their formation and evolution. Now, let's turn our attention to the invisible structures that cradle galaxies in their embrace, dark matter halos. These halos are vast, spherical clouds of dark matter that envelop galaxies, extending far beyond their visible edges. Though we cannot see them directly, their presence is felt through the gravitational influence they exert on the galaxies they surround. Think of dark matter halos as the unseen hands that hold galaxies together, shaping their growth and guiding their destiny. Dark matter halos form early in the universe's history, long before galaxies take shape. As the universe expands and cools, dark matter particles begin to clump together under the force of gravity. These clumps grow over time, merging with one another to form larger and larger structures. Eventually, they become massive enough to attract ordinary matter, gas and dust, into their gravitational grip. This is where the story of galaxy formation truly begins, as the dark matter halo acts as a cosmic cradle, drawing in the raw materials needed to build stars and galaxies. The size and mass of a dark matter halo play a critical role in determining the type of galaxy that forms within it. Smaller halos tend to host dwarf galaxies, while larger halos give rise to massive galaxies like our Milky Way. The halo's gravitational pull not only gathers gas and dust, but also shapes the galaxy's structure. For example, spiral galaxies, with their distinctive arms, owe their graceful forms to the way dark matter halos distribute gravity, creating the conditions for stars and gas to settle into rotating disks. But dark matter halos do more than just shape galaxies. They also influence their evolution. As galaxies grow and interact with one another, their dark matter halos play a key role in these cosmic encounters. When two galaxies collide, their halos merge, creating a new, larger halo that can trigger bursts of star formation or even reshape the galaxies themselves. Over time, these interactions help galaxies grow and evolve, transforming them from small, irregular collections of stars into the majestic structures we observe today. One of the most intriguing aspects of dark matter halos is their ability to persist over billions of years. Unlike ordinary matter, which can be heated, cooled, or blown away by cosmic events, dark matter remains largely unaffected. This stability allows halos to act as long-term anchors, providing a steady gravitational foundation for galaxies to grow and thrive. Without dark matter halos, galaxies would lack the stability needed to maintain their structure over cosmic timescales. As we explore the role of dark matter halos, it becomes clear that these invisible structures are not just passive bystanders. They are active participants in the life cycle of galaxies. From their formation in the early universe to their influence on galaxy evolution, dark matter halos are essential to understanding the cosmos. And as we continue to study them, we uncover more about the hidden forces that shape the universe, revealing the intricate interplay between the seen and the unseen. With this understanding of dark matter halos in place, let's now explore how gravity, working hand in hand with dark matter, shapes the distribution of galaxies across the universe. Now, let's take a closer look at the invisible force that binds the cosmos together: gravity. It's gravity that orchestrates the dance of galaxies, pulling them into clusters, shaping their paths, and determining their fate. But gravity doesn't work alone. In the grand cosmic ballet, dark matter plays a leading role, amplifying gravity's influence and ensuring that galaxies form and evolve as they do. At its core, gravity is the force that attracts matter to matter. It's what keeps planets orbiting stars, stars orbiting galaxies, and galaxies bound together in vast clusters. But when we zoom out to the scale of the universe, gravity's story becomes more complex. Here, dark matter steps in, adding its immense gravitational pull to the mix. While ordinary matter, the stuff we can see, makes up only a small fraction of the universe, dark matter is far more abundant. This means that dark matter's gravity dominates on cosmic scales, shaping the large-scale structure of the universe. Imagine the universe as a vast, invisible web, with dark matter forming the threads that hold everything together. These threads, or filaments, create a network of gravitational wells, pulling galaxies into clusters and superclusters. Without dark matter, this cosmic web wouldn't exist, and galaxies would be scattered randomly across the void. Instead, dark matter's gravity ensures that galaxies are distributed in a structured, almost orderly way, forming the intricate patterns we observe in the night sky. One of the most striking examples of gravity's role, powered by dark matter, is the formation of galaxy clusters. These clusters are the largest structures in the universe, containing hundreds or even thousands of galaxies bound together by gravity. Dark matter's gravitational pull is what holds these clusters together, preventing them from flying apart. In fact, the amount of dark matter in a cluster is so vast that it outweighs the visible matter by a factor of 5 to 1. This invisible scaffolding not only keeps galaxies clustered, but also influences their motion within the cluster, creating a dynamic and ever-changing cosmic environment. But gravity's influence doesn't stop at holding galaxies together. It also shapes their internal structure. For instance, the rotation of spiral galaxies is governed by the balance between gravity and the centrifugal force created by their spinning motion. Dark matter's gravitational pull ensures that stars and gas within these galaxies move in stable orbits, maintaining the galaxy's shape over billions of years. Without dark matter, galaxies would spin apart, their stars and gas flung into the void. Gravity also plays a crucial role in the interactions between galaxies. When galaxies collide, their dark matter halos merge, creating a new gravitational landscape. This merger can trigger bursts of star formation, reshape the galaxies involved, and even lead to the creation of entirely new structures. These interactions are a testament to the power of gravity, working hand in hand with dark matter to sculpt the universe on both large and small scales. As we explore the role of gravity in galaxy formation, it's clear that this fundamental force, amplified by dark matter, is the architect of the cosmos. From the smallest dwarf galaxies to the largest superclusters, gravity shapes the universe, ensuring that galaxies form, evolve, and interact in ways that continue to captivate and inspire us. And as we peer deeper into the cosmos, we uncover more about the delicate balance between gravity and dark matter, revealing the hidden forces that govern the universe's grand design. With this understanding of gravity's role in place, let's now turn our attention to how scientists use computer simulations to model the universe's formation, shedding light on the intricate interplay between dark matter and the cosmos. Now, let's step into the fascinating world of computer simulations, where scientists recreate the universe itself. These simulations are like cosmic laboratories, allowing us to explore how galaxies form and evolve over billions of years. At the heart of these models lies dark matter, the invisible force that shapes the universe on a grand scale. To understand how the universe came to be, scientists start by feeding vast amounts of data into powerful supercomputers. These computers use mathematical equations to simulate the behavior of matter, energy, and gravity over time. But here's the key ingredient: dark matter. Without it, the simulation simply wouldn't match what we observe in the real universe. Dark matter's gravitational pull is what guides the formation of galaxies, clusters, and the cosmic web, making it an essential part of the equation. One of the most remarkable aspects of these simulations is their ability to show how small fluctuations in the early universe grew into the structures we see today. Imagine the universe just after the Big Bang, a hot, dense soup of particles. Tiny ripples in this soup, caused by dark matter, began to grow under the influence of gravity. Over billions of years, these ripples evolved into the vast network of galaxies and clusters we observe today. Simulations allow us to watch this process unfold, step by step, revealing how dark matter's gravity shaped the cosmos. These virtual universes also help scientists test their theories. For example, by tweaking the amount of dark matter or its distribution, researchers can see how these changes affect galaxy formation. This process helps refine our understanding of dark matter's properties and its role in the universe. It's like running countless experiments, each one bringing us closer to unraveling the mysteries of the cosmos. One of the most striking results of these simulations is the way they mirror the real universe. When scientists compare their virtual galaxies to those observed by telescopes, the similarities are uncanny. Spiral galaxies, elliptical galaxies, and even the intricate filaments of the cosmic web all appear in the simulations, just as they do in the night sky. This remarkable agreement between theory and observation is a testament to the power of dark matter and the accuracy of these models. But simulations don't just confirm what we already know, they also reveal new insights. For instance, they've shown how dark matter halos influence the formation of galaxies, guiding the flow of gas and dust into the regions where stars are born. They've also shed light on the role of dark matter in galaxy collisions, showing how these events can trigger bursts of star formation or even create entirely new structures. As we continue to refine these simulations, they become even more detailed and accurate. With each advancement, we gain a deeper understanding of the universe's history and the forces that shaped it. These virtual explorations remind us that dark matter isn't just a theoretical concept. It's a fundamental part of the cosmos, shaping everything from the smallest galaxies to the largest structures in the universe. With this glimpse into the world of simulations, we're ready to explore another piece of the cosmic puzzle, the mystery of the missing mass and how it led scientists to uncover the existence of dark matter. Now, let's turn our attention to one of the most intriguing puzzles in modern astronomy, the missing mass problem. This mystery began to unfold in the early 20th century, when scientists noticed something strange about the way galaxies behaved. According to the laws of physics, the stars in a galaxy should orbit its center in a predictable way, with those closer to the center moving faster than those farther out. But when astronomers measured the speeds of stars in galaxies, they found something unexpected. The stars on the outer edges of galaxies were moving just as fast as those near the center, defying the predictions of Newtonian gravity. This discrepancy suggested that there was far more mass in galaxies than what could be accounted for by the visible stars, gas, and dust. But where was this missing mass? The answer to this question came from a groundbreaking discovery in the 1970s, when astronomer Vera Rubin and her colleagues studied the rotation curves of galaxies. A rotation curve is a graph that shows how fast stars and gas move at different distances from a galaxy's center. What Rubin found was astonishing. Instead of slowing down as they moved farther from the center, the stars and gas maintained high speeds, even at great distances. This observation could only be explained if there was an enormous amount of invisible matter surrounding the galaxy, exerting a gravitational pull on the stars. This invisible matter, which we now call dark matter, was the key to solving the missing mass problem. But how could something invisible have such a profound effect on the motion of stars? The answer lies in gravity. Dark matter doesn't emit, absorb, or reflect light, making it impossible to see with telescopes. Yet, it interacts with ordinary matter through gravity, shaping the way galaxies rotate and move. The presence of dark matter creates a gravitational field that extends far beyond the visible edges of galaxies, explaining why stars on the outskirts move so quickly. Without dark matter, the observed rotation curves simply wouldn't make sense. This discovery didn't just solve the missing mass problem, it revolutionized our understanding of the universe. It showed that the cosmos is filled with far more matter than we can see, and that this invisible substance plays a crucial role in shaping the structures we observe. The evidence from galaxy rotation curves was so compelling that it convinced many scientists of dark matter's existence, even though we still can't directly detect it. It's a reminder that sometimes the most profound discoveries come not from what we can see, but from what we can infer through careful observation and reasoning. As we continue to explore the cosmos, the missing mass problem remains a cornerstone of dark matter research. It's a testament to the power of curiosity and the importance of questioning what we think we know. And as we'll see next, this mystery is just one piece of a much larger puzzle, one that connects galaxies, clusters, and the very fabric of the universe itself. Now, let's zoom out from individual galaxies and explore the vast cosmic neighborhoods known as galaxy clusters. These clusters are among the largest structures in the universe, containing hundreds or even thousands of galaxies bound together by gravity. But what keeps these colossal gatherings from flying apart? The answer, once again, lies in the invisible hand of dark matter. Galaxy clusters are not just random collections of galaxies. They are held together by an immense gravitational force, and much of that force comes from dark matter. In fact, dark matter makes up about 85% of the total mass in a galaxy cluster. This invisible substance forms a massive, diffuse halo that envelops the entire cluster, creating a gravitational scaffold that holds everything in place. Without dark matter, the galaxies within these clusters would simply drift apart, unable to stay bound together by the gravity of the visible matter alone. But dark matter's role doesn't stop there. It also influences the behavior of galaxy clusters in fascinating ways. For example, when galaxy clusters collide, something extraordinary happens. The visible matter gas, stars, and dust interacts and slows down due to friction, often forming spectacular shock waves and hot gas clouds that emit X-rays. Dark matter, on the other hand, doesn't interact in the same way. It passes right through the collision, unaffected by these forces, This unique behavior was first observed in the famous bullet cluster, where the separation of dark matter and ordinary matter provided some of the strongest evidence for dark matter's existence. The presence of dark matter also affects how galaxy clusters evolve over time. As clusters grow by merging with smaller groups of galaxies, dark matter helps shape their structure and distribution. It acts as a cosmic glue, pulling galaxies together and guiding their movements. This process not only determines the layout of galaxy clusters, but also influences the formation of new stars and galaxies within them. In a sense, dark matter is the unseen architect of these massive cosmic cities, shaping their growth and development over billions of years. Understanding the role of dark matter in galaxy clusters is crucial for piecing together the larger story of the universe. These clusters are like cosmic laboratories, offering us a glimpse into the interplay between dark matter and ordinary matter on a grand scale. By studying them, we can learn more about how the universe's largest structures formed and how they continue to evolve. And as we'll see next, this exploration takes us even deeper into the mysteries of dark matter and its profound influence on the cosmos. Now, let's turn our attention to one of the most compelling pieces of evidence for dark matter's existence: the bullet cluster. This remarkable cosmic phenomenon offers a rare and vivid glimpse into the behavior of dark matter during galaxy collisions. The bullet cluster is actually two galaxy clusters that have collided, creating a cosmic spectacle that has captivated astronomers and deepened our understanding of the universe. When these two clusters collided, something extraordinary happened. The ordinary matter, gas, stars, and dust, interacted and slowed down due to friction, creating shock waves and heating up to emit X-rays. This hot gas, visible through X-ray telescopes, forms a bright, glowing cloud between the two clusters. But here's where it gets fascinating. While the ordinary matter was slowed and compressed, the dark matter behaved entirely differently. It passed right through the collision, unaffected by the forces that slowed the gas and stars. This separation between dark matter and ordinary matter was detected using a technique called gravitational lensing, which maps the distribution of mass by observing how light from distant objects is bent by gravity. The result, the dark matter from both clusters continued on its path, leaving the ordinary matter behind. This separation is like watching two clouds of smoke pass through each other, with one cloud continuing on as if nothing happened. The bullet cluster provides a striking visual representation of dark matter's unique properties: its invisibility, its lack of interaction with light, and its dominance in shaping the gravitational landscape of the universe. This observation is more than just a cosmic curiosity. It's one of the strongest pieces of evidence we have for the existence of dark matter. The fact that dark matter and ordinary matter behave so differently during a collision confirms that dark matter is not just an abstract idea. It's a real, physical component of the universe. The bullet cluster has become a cornerstone in our understanding of dark matter, helping to solidify its role in the cosmic framework. As we continue to study phenomena like the bullet cluster, we gain deeper insights into the invisible forces that shape our universe. These collisions are not just destructive events, they're also windows into the hidden workings of the cosmos. And as we'll see next, this exploration takes us even further into the mysteries of dark matter and its profound influence on the formation and evolution of galaxies. Now, let's shift our gaze to the stars, those shimmering beacons of light scattered across the night sky. Have you ever wondered how these stars come to be? The answer lies not just in the swirling clouds of gas and dust we can see, but also in the invisible embrace of dark matter. Dark matter plays a crucial role in setting the stage for star formation, acting as the unseen architect that shapes the conditions necessary for stars to ignite and shine. Imagine a galaxy as a vast, swirling dance floor. The visible matter, gas, dust, and stars, moves to the rhythm of gravity, but it's dark matter that provides the foundation for this cosmic ballet. Dark matter halos, those invisible structures surrounding galaxies, create the gravitational scaffolding that pulls gas and dust together. Without this gravitational pull, the gas would remain too diffuse, unable to clump together and collapse into the dense clouds needed to form stars. Here's how it works. As gas and dust are drawn into the gravitational wells created by dark matter, they begin to accumulate in dense regions. Over time, these regions grow denser and hotter, eventually reaching a point where the pressure and temperature are high enough to trigger nuclear fusion, the process that powers stars. In essence, dark matter acts as a cosmic gatherer, collecting the raw materials needed for star formation and creating the environments where stars can be born. But dark matter's influence doesn't stop there. It also helps regulate the pace of star formation. In galaxies with more dark matter, the gravitational pull is stronger, leading to more rapid and intense star formation. In contrast, galaxies with less dark matter may form stars more slowly or sporadically. This delicate balance between dark matter and ordinary matter ensures that star formation occurs in a controlled and sustainable manner, shaping the evolution of galaxies over billions of years. Interestingly, dark matter's role in star formation also helps explain why some galaxies are brimming with young, bright stars, while others are quieter and more subdued. In galaxies where dark matter dominates, the gravitational forces are strong enough to keep gas and dust tightly bound, fostering continuous star formation. In galaxies with less dark matter, the gas may be more easily dispersed, leading to fewer stars being born. As we explore the intricate relationship between dark matter and star formation, we begin to see how this invisible force is not just a passive bystander in the universe. It's an active participant, shaping the very fabric of galaxies and lighting up the cosmos with countless stars. And as we'll discover next, this influence extends even further, touching on the very shapes and structures of galaxies themselves. Now, let's bring our cosmic journey closer to home and take a closer look at our very own galaxy, the Milky Way. Just like other galaxies, the Milky Way is deeply intertwined with dark matter, an invisible force that shapes its structure and guides its motion through the cosmos. At the heart of the Milky Way lies a supermassive black hole, surrounded by a swirling disk of stars, gas, and dust. But what holds this entire system together? The answer, once again, is dark matter. Our galaxy is enveloped in a vast, invisible halo of dark matter that extends far beyond the visible stars and gas. This halo acts as a gravitational anchor, keeping the Milky Way's spiral arms intact and ensuring that stars and gas clouds move in predictable orbits. Without this dark matter halo, the Milky Way would simply fly apart, its stars scattering into the void. One of the most fascinating ways dark matter influences the Milky Way is through its effect on the galaxy's rotation. When astronomers first measured the speed at which stars orbit the center of the Milky Way, they noticed something unexpected. The outer stars were moving much faster than they should have been, based on the amount of visible matter in the galaxy. This discrepancy was one of the first clues that dark matter exists. The invisible halo of dark matter provides the extra gravitational pull needed to explain these high speeds, ensuring that stars on the outskirts of the galaxy don't drift away. But dark matter's role doesn't stop at rotation. It also plays a key part in shaping the Milky Way's overall structure. The gravitational pull of dark matter helps maintain the galaxy's spiral arms, those beautiful, curving lanes of stars and gas that give the Milky Way its distinctive appearance. These arms are not static. They ripple and move, influenced by the gravitational tug of dark matter and the interactions between stars and gas. Dark matter acts as a stabilizing force, ensuring that the spiral arms remain coherent over billions of years. Interestingly, dark matter also influences the distribution of stars within the Milky Way. In regions where dark matter is more concentrated, stars tend to cluster more densely. This clustering affects how stars form and evolve, creating pockets of intense star formation and shaping the galaxy's overall stellar population. Without dark matter, the Milky Way's stars would be spread more evenly, and the galaxy would look very different from the vibrant, structured spiral we see today. As we peer deeper into the Milky Way's mysteries, it becomes clear that dark matter is not just a distant, abstract concept. It's a fundamental part of our galactic home. From holding the galaxy together to shaping its rotation and structure, dark matter is the unseen force that keeps the Milky Way spinning through the cosmos. And as we'll explore next, this influence extends even further, reaching into the smallest and faintest galaxies in the universe. Now, let's turn our attention to the smallest members of the cosmic family, dwarf galaxies. These tiny galaxies, often containing only a few billion stars, are fascinating not just for their size, but for the outsized role dark matter plays in their existence. While they may seem insignificant compared to giants like the Milky Way, dwarf galaxies hold some of the most compelling clues about the nature of dark matter and its influence on the universe. Dwarf galaxies are unique because they are dominated by dark matter. In fact, dark matter makes up the vast majority of their mass, far outweighing the visible stars and gas. This dominance is so extreme that in some dwarf galaxies, dark matter accounts for more than 90% of their total mass. But why is this the case? The answer lies in their formation and evolution. Unlike larger galaxies, which have enough visible matter to form dense, bright structures, dwarf galaxies are so small that their gravitational pull isn't strong enough to hold onto much gas and dust. As a result, they end up with very little ordinary matter, leaving dark matter as the primary force shaping their behavior. One of the most striking examples of dark matter's influence on dwarf galaxies can be seen in their rotation. Just like in larger galaxies, Stars in dwarf galaxies orbit around their centers. But here's the twist. The outer stars in these galaxies move at speeds that can't be explained by the visible matter alone. This discrepancy is even more pronounced in dwarf galaxies than in larger ones, providing some of the strongest evidence for dark matter's existence. The invisible gravitational pull of dark matter keeps these stars in orbit, preventing them from drifting away into the void. Another fascinating aspect of dwarf galaxies is their distribution in the universe. They are often found orbiting larger galaxies, like satellites around a planet. This arrangement is no accident. It's a direct result of dark matter's gravitational influence. The dark matter halos of larger galaxies act like cosmic nets, capturing smaller galaxies and pulling them into orbit. Over time, these dwarf galaxies become part of the larger galaxy system, contributing to its overall structure and evolution. But dwarf galaxies aren't just passive players in the cosmic dance. They also play a crucial role in helping scientists understand dark matter. Because they are so rich in dark matter and relatively simple in structure, they serve as natural laboratories for studying its properties. By observing how stars move within dwarf galaxies, astronomers can map the distribution of dark matter and test theories about its behavior. These observations have led to some surprising discoveries, such as the fact that dark matter in dwarf galaxies seems to be more concentrated in their centers than in larger galaxies. The relationship between dark matter and dwarf galaxies also sheds light on the early universe. Many dwarf galaxies are thought to be relics from the universe's infancy, having formed when the cosmos was still young. Their dark matter content provides a glimpse into the conditions that existed billions of years ago, offering clues about how galaxies first began to form. By studying these tiny galaxies, scientists can piece together the story of how dark matter shaped the universe from its earliest moments. As we explore the mysteries of dwarf galaxies, it becomes clear that their small size belies their immense importance. They are not just cosmic curiosities, they are key to understanding the role of dark matter in the universe. From their rotation to their distribution and their origins, dwarf galaxies reveal the profound influence of this invisible force. And as we'll see next, this influence extends even further, shaping the behavior of some of the universe's most extreme objects, black holes. Now, let's shift our gaze to the cutting-edge efforts to uncover the secrets of dark matter. Despite its invisible nature, scientists have developed ingenious methods to detect and study this elusive substance, using tools that range from massive underground detectors to powerful telescopes and high-energy particle colliders. Each approach offers a unique window into the mystery of dark matter, bringing us closer to understanding its true nature. One of the most direct methods involves particle detectors buried deep underground. These experiments are designed to catch rare interactions between dark matter particles and ordinary matter. By shielding the detectors from cosmic rays and other background noise, scientists hope to spot the faint signals that dark matter might leave behind. Imagine a dark, quiet room where even the tiniest whisper could be heard. That's the environment these detectors create, waiting patiently for a glimpse of the invisible. Telescopes, on the other hand, allow us to study dark matter indirectly by observing its effects on the cosmos. by mapping the way light bends around massive objects, a phenomenon known as gravitational lensing. Astronomers can infer the presence of dark matter. This technique has revealed vast halos of dark matter surrounding galaxies and even entire clusters of galaxies. It's like seeing the shadow of something you can't see directly, a cosmic detective story unfolding across the universe. Particle colliders, like the Large Hadron Collider, take a different approach. These machines smash particles together at incredibly high speeds, recreating conditions similar to those in the early universe. The goal is to produce dark matter particles, even if only for a fleeting moment, and study their properties. While no direct detection has been made yet, these experiments have narrowed down the possibilities, helping scientists refine their theories about what dark matter might be. Each of these methods has its strengths and challenges, but together, they form a comprehensive toolkit for exploring the unknown. From the depths of the Earth to the farthest reaches of space, the search for dark matter is a testament to human ingenuity and curiosity. And as we continue to push the boundaries of science, we inch closer to unraveling one of the universe's greatest mysteries. Next, we'll explore the leading candidates for dark matter particles and why they hold so much promise in this ongoing quest. Now, let's turn our attention to the leading candidates that scientists believe could make up dark matter. Among the most promising are WIMP, or weakly interacting massive particles, and actions. These hypothetical particles are at the forefront of dark matter research, offering potential explanations for the invisible force shaping our universe. WIMP are thought to be heavy particles that interact with ordinary matter only through gravity and the weak nuclear force, one of the four fundamental forces of nature. This weak interaction makes them incredibly difficult to detect, but their existence would neatly explain many of the observed effects of dark matter. For instance, WIMP could account for the way galaxies rotate and how galaxy clusters hold together. Their mass and behavior align with predictions from cosmological models, making them a strong contender in the search for dark matter. On the other hand, actions are much lighter particles, originally proposed to solve a different problem in particle physics related to the behavior of quarks. Unlike WIMP, actions are extremely low mass and interact even more weakly with ordinary matter. Despite their lightness, actions could still make up a significant portion of dark matter if they exist in vast numbers. Their unique properties make them another compelling candidate, and experiments are underway to detect their faint signals. Both WIMP and actions are appealing because they fit well within the framework of existing physics theories, such as the Standard Model of particle physics and its extensions. While neither has been directly observed yet, their theoretical foundations make them prime targets for ongoing experiments. From underground detectors searching for WIMP to specialized instruments designed to capture actions, the hunt for these particles is a major focus of modern astrophysics. As we continue to explore these possibilities, the search for WIMP and actions represents a fascinating intersection of theory and experimentation. Each discovery, or even the absence of one, brings us closer to understanding the true nature of dark matter. Next, we'll delve into how dark matter influenced the early universe, shaping the first galaxies and setting the stage for the cosmos we see today. To understand the profound role of dark matter in the cosmos, we must journey back to the very beginning, the early universe. Picture a time when the universe was a hot, dense soup of particles, just moments after the Big Bang. In this primordial chaos, dark matter was already at work, quietly shaping the future of everything we see today. As the universe expanded and cooled, ordinary matter, the stuff that makes up stars, planets, and us, began to clump together under the influence of gravity. But here's the twist. Dark matter, invisible and mysterious, was already forming vast, web-like structures. These dark matter filaments acted as a cosmic scaffold, guiding the distribution of ordinary matter and setting the stage for the first galaxies to form. Without dark matter, the universe as we know it might never have come to be. Its gravitational pull provided the necessary framework for gas and dust to gather, eventually collapsing into the dense clouds that ignited the first stars. These early stars, in turn, lit up the darkness, creating the building blocks for galaxies, galaxy clusters, and the intricate cosmic web we observe today. What's truly fascinating is how dark matter's influence persisted over billions of years. As galaxies grew and evolved, dark matter continued to shape their structures, forming the halos that surround them and influencing their movements. Even now, dark matter remains the unseen architect of the cosmos, holding galaxies together and guiding their interactions on the grandest scales. This early interplay between dark matter and ordinary matter laid the foundation for the universe's evolution. It's a story of collaboration between the visible and the invisible, where dark matter's quiet dominance set the stage for the vibrant, star-filled cosmos we inhabit today. Next, we'll explore how dark matter's role extends even further, influencing the universe's expansion and its ultimate fate. Now, let's turn our gaze to the broader canvas of the universe and examine how dark matter intertwines with one of the most profound mysteries of all cosmic expansion. As the universe stretches and grows, dark matter plays a pivotal role in this grand dance, working alongside its enigmatic counterpart, dark energy, to shape the fate of the cosmos. Imagine the universe as a vast, ever-expanding balloon. Galaxies are like dots on its surface, drifting apart as the balloon inflates. But what drives this expansion? Scientists have discovered that dark energy, a mysterious force permeating space, is responsible for accelerating this process. Yet, dark matter, with its immense gravitational influence, acts as a counterbalance, pulling galaxies and galaxy clusters together, even as the universe stretches outward. This delicate interplay between dark matter and dark energy is what shapes the large-scale structure of the universe. Dark matter's gravitational pull creates the cosmic web, the intricate network of filaments that connect galaxies and galaxy clusters. Meanwhile, dark energy pushes space itself apart, causing the universe to expand at an ever-increasing rate. Together, these two forces dictate how galaxies move, how they cluster, and how the universe evolves over time. One of the most intriguing aspects of this relationship is how it influences the universe's ultimate fate. Will the expansion continue indefinitely, leading to a cold, dark, and empty cosmos? Or will dark matter's gravitational pull eventually slow things down, altering the trajectory of cosmic evolution? These are questions that scientists are still working to answer, and they highlight the profound connection between dark matter and the universe's expansion. As we peer deeper into the cosmos, we begin to see how dark matter and dark energy are not just isolated phenomena, but integral parts of a larger cosmic story. They are the unseen forces that shape the universe's past, present, and future, guiding its evolution in ways we are only beginning to understand. Next, we'll delve into the theories that challenge our understanding of dark matter and explore the possibilities that lie beyond its mysterious veil. While dark matter remains the leading explanation for the mysteries of the cosmos, some scientists have proposed alternative theories that challenge this widely accepted idea. One of the most prominent alternatives is modified Newtonian dynamics, or MIND. This theory suggests that instead of invoking invisible dark matter, we might need to rethink our understanding of gravity itself. According to MIND, the laws of gravity behave differently on the vast scales of galaxies and galaxy clusters, which could explain the observed motions of stars and galaxies without the need for dark matter. MIND has had some success in explaining the rotation curves of galaxies, particularly in cases where dark matter models struggle. However, it faces significant challenges when applied to larger structures like galaxy clusters or the cosmic web. While it can account for the behavior of individual galaxies, it struggles to explain the gravitational lensing effects observed in massive clusters, where the bending of light suggests the presence of far more mass than visible matter alone can provide. This has led many scientists to view MIND as an incomplete solution, though it remains an intriguing alternative worth exploring. Another approach to explaining the universe's missing mass involves tweaking Einstein's theory of general relativity. Some researchers propose that gravity might operate differently on cosmic scales, with modifications to the equations that govern how massive objects interact. These theories, often referred to as modified gravity, aim to account for the observed phenomena without relying on dark matter. While they offer a fresh perspective, they too face hurdles, particularly when trying to reconcile their predictions with the precise measurements of the cosmic microwave background radiation, which strongly supports the existence of dark matter. Despite these challenges, the exploration of alternative theories is vital to the scientific process. It pushes us to question our assumptions and refine our understanding of the universe. While dark matter remains the most widely accepted explanation, these alternatives remind us that science is a journey of discovery, where even the most established ideas can be re-examined and reimagined. As we continue to probe the cosmos, we may find that the truth lies somewhere between these competing theories, or perhaps in an entirely new framework we have yet to imagine. Next, we'll explore how dark matter influences the shapes and structures of galaxies, revealing its subtle yet profound impact on the universe's grand design. Now, let's turn our attention to how dark matter shapes the very forms of galaxies, sculpting them into the stunning structures we observe across the cosmos. Dark matter's gravitational influence is not just a background force. It actively molds galaxies, determining whether they become elegant spirals, smooth ellipticals, or something in between. To understand this, Picture a galaxy as a dance of stars, gas, and dust, all moving under the guidance of gravity. But here's the twist. Dark matter is the unseen choreographer, setting the rhythm and flow of this cosmic ballet. In spiral galaxies, like our own Milky Way, dark matter forms a vast, invisible halo that extends far beyond the visible disk. This halo provides the gravitational framework that keeps the galaxy's arms tightly wound, allowing stars and gas to orbit in graceful, swirling patterns. Without dark matter, these delicate spirals might unravel, losing their iconic shapes. Elliptical galaxies, on the other hand, tell a different story. These galaxies are often older and more massive, with stars moving in more random, less organized orbits. Dark matter plays a crucial role here too, but its influence is subtler. In these systems, dark matter helps stabilize the galaxy's structure, preventing it from collapsing or flying apart. The result is a smooth, rounded shape, like a glowing cosmic egg, where stars are evenly distributed rather than arranged in arms. Interestingly, dark matter also affects the formation of irregular galaxies, which lack the symmetry of spirals or ellipticals. These galaxies often result from collisions or interactions with other galaxies, and dark matter's gravitational pull can amplify these chaotic events, leading to unique and unpredictable shapes. In some cases, dark matter can even strip away gas and stars from smaller galaxies, leaving behind ghostly trails of matter that hint at its invisible presence. The shapes of galaxies, then, are not just a matter of chance. They are a direct reflection of dark matter's hidden hand. Whether a galaxy becomes a spiral, an elliptical, or something entirely different depends on how dark matter interacts with the visible components over billions of years. This interplay between the seen and the unseen is one of the most fascinating aspects of galaxy formation, revealing just how deeply dark matter is woven into the fabric of the universe. As we continue our journey, we'll explore how dark matter's influence extends even further, shaping not just individual galaxies, but the vast networks that connect them across the cosmos. Now, let's venture into the mysterious interplay between dark matter and one of the universe's most enigmatic phenomena, black holes. While black holes are often thought of as cosmic vacuum cleaners, devouring everything in their path, their relationship with dark matter is far more subtle and intriguing. Dark matter, with its invisible gravitational pull, doesn't just shape galaxies, it also plays a role in the birth and behavior of black holes. Imagine a black hole forming at the heart of a galaxy. As stars collapse and gas clouds condense, dark matter's gravitational influence helps guide this process. The dense regions of dark matter, known as halos, create the perfect environment for black holes to form. These halos act like cosmic scaffolding, pulling in matter and energy, and providing the gravitational stability needed for a black hole to emerge. In this way, dark matter doesn't just coexist with black holes, it actively contributes to their creation. But the relationship doesn't end there. Once a black hole forms, dark matter continues to shape its behavior. For instance, dark matter can accumulate around a black hole, creating a dense, invisible cloud. This cloud can influence how the black hole grows, feeding it with additional material over time. Some scientists even speculate that dark matter could be a key ingredient in the formation of supermassive black holes, the giants that lurk at the centers of galaxies. Without dark matter's gravitational assistance, these colossal objects might never reach their staggering sizes. Interestingly, dark matter might also affect how black holes interact with their surroundings. As black holes move through their galaxies, they can drag dark matter along with them, creating ripples in the cosmic web. These ripples could influence the distribution of stars and gas, subtly altering the galaxy's structure. In some cases, dark matter might even slow down or redirect the paths of black holes, shaping their trajectories in ways we're only beginning to understand. Yet, despite these fascinating connections, much about the relationship between dark matter and black holes remains a mystery. For example, could dark matter itself be consumed by black holes? Some theories suggest that dark matter particles might interact with black holes in unique ways, potentially revealing clues about their nature. While we don't yet have definitive answers, the study of this cosmic duo continues to push the boundaries of our understanding. As we explore further, we'll see how dark matter's influence extends beyond individual black holes, shaping the larger structures of the universe. But for now, let's marvel at the intricate dance between these two cosmic forces, one invisible, the other inescapable, and how together they weave the fabric of the cosmos. As we peer into the horizon of cosmic discovery, the future of dark matter research holds immense promise. Scientists around the world are gearing up for groundbreaking experiments and deploying cutting-edge technologies to unravel the mysteries of this elusive substance. One of the most anticipated projects is the Large Synoptic Survey Telescope, or LSST, set to begin its observations in the coming years. This powerful telescope will map the night sky in unprecedented detail, capturing the subtle gravitational effects of dark matter on light from distant galaxies. By analyzing these distortions, researchers hope to piece together a clearer picture of how dark matter is distributed across the universe. Another exciting frontier lies in the realm of particle physics. Deep underground, experiments like the LUX Zeppelin and Xenon collaborations are searching for direct evidence of dark matter particles. These detectors, shielded from cosmic rays and other interference, are designed to catch the faintest signals of dark matter interacting with ordinary matter. If successful, these experiments could finally identify the particles that make up dark matter, answering one of the most profound questions in modern science. Meanwhile, space-based missions are also joining the hunt. The European Space Agency's Euclid mission, set to launch in the near future, aims to study the large-scale structure of the universe. By mapping the distribution of galaxies and measuring the effects of dark energy and dark matter, Euclid could provide critical insights into how these invisible forces shape the cosmos. Similarly, NASA's Nancy Grace Roman Space Telescope will explore the universe's expansion and the role of dark matter in galaxy formation, offering a complementary perspective to ground-based observations. Advancements in computing and simulation technology are also revolutionizing dark matter research. Supercomputers are now capable of running highly detailed simulations of the universe's evolution, incorporating dark matter's influence on galaxy formation and cosmic structure. These simulations allow scientists to test theories and make predictions that can be compared with real-world observations, refining our understanding of dark matter's role in the cosmos. As these efforts converge, the next decade could bring transformative breakthroughs, from detecting dark matter particles to mapping its cosmic web. The tools and technologies at our disposal are more powerful than ever. Yet, the journey is far from over. Each discovery raises new questions, driving the quest for knowledge ever forward. With every experiment and observation, we inch closer to uncovering the secrets of dark matter, bringing us one step closer to understanding the universe's hidden architecture. Looking ahead, the future of dark matter research is not just about solving a scientific puzzle, it's about expanding the boundaries of human knowledge. As we continue to explore, we're reminded that the universe is full of wonders waiting to be discovered, and dark matter is just one of the many mysteries that beckon us to look deeper. As we venture into the realm of the multiverse, the role of dark matter takes on an even more intriguing dimension. Imagine a vast cosmic tapestry where countless universes exist alongside our own, each with its own unique laws of physics and structures. In this grand multiverse theory, dark matter could serve as a hidden thread, weaving connections between these parallel worlds. While the idea of multiple universes might sound like science fiction, it's a concept that some physicists take seriously, and dark matter could play a pivotal role in shaping this cosmic landscape. One possibility is that dark matter acts as a bridge between universes, influencing the way they interact or even collide. In some theories, dark matter particles could traverse the boundaries between universes, carrying information or energy from one to another. This could explain why dark matter seems so elusive in our own universe. It might not entirely belong here. Instead, it could be a remnant of interactions with other universes, leaving behind traces that we're only beginning to detect. Another fascinating idea is that dark matter could be a key ingredient in the formation of universes themselves. In the multiverse scenario, new universes might constantly be born, each with its own balance of dark matter and ordinary matter. The amount and distribution of dark matter in a universe could determine its structure, from the formation of galaxies to the very fabric of space and time. In this way, dark matter might not just shape our universe, but could be a fundamental force in the creation of countless others. Of course, these ideas are still speculative, and the multiverse remains one of the most debated topics in modern physics. Yet, the connection between dark matter and the multiverse offers a tantalizing glimpse into the possibilities that lie beyond our current understanding. If dark matter does indeed play a role in connecting universes, it could open up entirely new avenues of exploration, challenging us to rethink the nature of reality itself. As we ponder these cosmic mysteries, one thing becomes clear. Dark matter is not just a puzzle to be solved within our own universe. It might hold the key to understanding a much larger, more complex cosmic reality, one where the boundaries between universes blur and the secrets of existence stretch far beyond what we can currently imagine. The journey to uncover these truths is just beginning, and with each discovery, we move closer to unraveling the profound mysteries of the multiverse. Now, let's shift our gaze from the cosmic mysteries of the multiverse to something a little closer to home: how dark matter has captured the imagination of storytellers and creators in popular culture. From blockbuster movies to best-selling novels, dark matter has become a fascinating subject that bridges the gap between science and fiction, shaping how the public perceives this elusive cosmic phenomenon. In movies, dark matter often takes on a larger-than-life role, portrayed as a mysterious force with the power to warp reality or unlock unimaginable technologies. Films like Interstellar and The Dark Matter use it as a central plot device, weaving it into stories of space exploration and human survival. These portrayals, while sometimes exaggerated, spark curiosity and wonder, inviting audiences to ponder the real science behind the fiction. They also highlight how dark matter, despite being invisible and intangible, can inspire awe and intrigue on the big screen. Books, too, have embraced dark matter as a rich source of inspiration. Science fiction authors like Philip Pullman, in his Dark Materials trilogy, use dark matter, or dust, as he calls it, to explore themes of consciousness, morality, and the nature of existence. These stories often take creative liberties, but they also reflect the profound questions that dark matter raises about the universe and our place within it. By blending science with imagination, these narratives make complex ideas more accessible, encouraging readers to think deeply about the cosmos. Even in video games and television shows, dark matter has found a place as a symbol of the unknown. Games like Mass Effect and series like Doctor Who incorporate it into their lore, often as a source of power or danger. These portrayals, while not always scientifically accurate, play a crucial role in shaping public perception. They introduce dark matter to audiences who might not encounter it in a classroom or a textbook, sparking interest and conversation about the real science behind the fiction. But what does this mean for how we understand dark matter in the real world? While popular culture often takes creative liberties, it also serves as a gateway to scientific curiosity. When a movie or book introduces dark matter, it invites viewers and readers to ask questions, seek answers, and engage with the science in a way that feels personal and exciting. This blending of fact and fiction can inspire the next generation of scientists, encouraging them to explore the mysteries of the universe with fresh eyes and boundless imagination. As we reflect on dark matter's role in popular culture, it's clear that its influence extends far beyond the realm of physics. It has become a symbol of the unknown, a canvas for creativity, and a bridge between science and storytelling. Whether on the screen, the page, or in our imaginations, dark matter continues to captivate and inspire, reminding us that the mysteries of the universe are as much about wonder as they are about discovery. And as we move forward, this interplay between science and culture will undoubtedly shape how we perceive and ultimately understand the cosmos. As we step away from the vibrant world of popular culture and back into the realm of science, we're reminded of one undeniable truth: dark matter remains one of the greatest mysteries of the universe. Despite decades of research, countless experiments, and groundbreaking discoveries, we still don't fully understand what dark matter is or how it behaves. This enduring enigma is what keeps scientists around the world captivated, driving them to push the boundaries of human knowledge in search of answers. Think about it. Dark matter makes up roughly 85% of the universe's total mass, yet it doesn't interact with light, making it invisible to our most powerful telescopes. We can't see it, touch it, or detect it directly. Instead, we know it exists because of its gravitational effects on galaxies and galaxy clusters. It's like trying to solve a puzzle with most of the pieces missing. Every discovery brings us closer to understanding, but it also reveals new questions, deepening the mystery even further. What makes dark matter so fascinating is not just what we don't know, but what it represents, a challenge to our understanding of the universe. For centuries, humans have looked to the stars, seeking to unravel the secrets of the cosmos. Dark matter reminds us that there's still so much to learn, and that the universe is far more complex and wondrous than we ever imagined. It's a humbling reminder that, even with all our advancements, we're still just beginning to scratch the surface of cosmic knowledge. This mystery also fuels innovation. The search for dark matter has led to the development of cutting-edge technologies, from ultra-sensitive particle detectors to advanced telescopes that peer into the farthest reaches of space. These tools not only help us study dark matter, but also open new doors for exploring other cosmic phenomena. In a way, the pursuit of dark matter is driving the future of science itself, inspiring breakthroughs that could transform our understanding of the universe. Yet, for all the progress we've made, dark matter continues to elude us. Is it made of particles we haven't yet discovered? Could it be part of a larger, more complex framework of physics that we're only beginning to grasp? Or is it something entirely different, beyond our current understanding? These questions don't just challenge scientists, they invite all of us to wonder, to imagine, and to dream about the possibilities. And that's the beauty of dark matter. It's not just a scientific problem to be solved, it's a source of inspiration. It reminds us that the universe is full of mysteries waiting to be uncovered, and that the journey of discovery is just as important as the answers we seek. As we continue to explore the cosmos, dark matter stands as a symbol of the unknown, a reminder that there's always more to learn, more to discover, and more to marvel at in the vast, wondrous expanse of the universe. Now, let's shift our gaze from the scientific pursuit of dark matter to its profound influence on human creativity and imagination. Dark matter, with its elusive nature and cosmic significance, has become more than just a scientific mystery. It's a wellspring of inspiration for artists, philosophers, and storytellers alike. Its very invisibility and the questions it raises about the universe have sparked countless works of art, literature, and thought, inviting us to explore the boundaries of what we know and what we can imagine. In the realm of art, dark matter has inspired breathtaking visual representations. Artists often use it as a metaphor for the unseen forces that shape our lives, creating pieces that evoke the mystery and vastness of the cosmos. Imagine a painting where swirling galaxies are held together by invisible threads of dark matter, or a sculpture that captures the tension between the seen and the unseen. These works remind us that there's beauty in the unknown, and that even the things we can't perceive play a vital role in the grand tapestry of existence. Philosophers, too, have been drawn to the enigma of dark matter. It challenges our understanding of reality, prompting questions about the nature of existence, the limits of human knowledge, and the relationship between the visible and the invisible. Dark matter serves as a powerful symbol of the mysteries that lie beyond our grasp, encouraging us to think deeply about our place in the universe. It's a reminder that not everything can be explained or understood, and that sometimes the most profound truths are hidden in the shadows. Storytelling, perhaps more than any other medium, has embraced dark matter as a source of endless possibilities. Science fiction writers, in particular, have woven it into their narratives, using it to explore themes of discovery, exploration, and the unknown. From novels that imagine civilizations thriving in dark matter, rich regions of space, to films that depict its effects on time and reality, dark matter has become a cornerstone of speculative fiction. It allows storytellers to push the boundaries of imagination, creating worlds where the rules of physics are bent and the impossible becomes possible. But dark matter's influence extends beyond fiction. It also inspires us to dream about the future of science and exploration. What if we could one day harness dark matter's energy? What if we discovered that it holds the key to understanding the origins of the universe? These questions fuel our curiosity and drive us to keep exploring, not just as scientists, but as dreamers and creators. In many ways, dark matter is a mirror reflecting our own creativity and imagination. It challenges us to think beyond the visible, to question what we know, and to imagine what might be. It reminds us that the universe is not just a collection of stars and planets, but a canvas for our ideas, our stories, and our dreams. And as we continue to explore its mysteries, we're not just uncovering the secrets of the cosmos, we're also discovering new ways to express the boundless potential of the human mind. As we step into the final chapter of our cosmic journey, let us pause and marvel at the sheer beauty of the universe. Picture a vast, endless expanse where galaxies swirl like delicate brushstrokes on a canvas, each one a masterpiece of light, color, and mystery. These galaxies, from the grand spirals to the compact ellipticals, are not just random collections of stars. They are the result of an intricate dance, choreographed by the invisible hand of dark matter. Imagine standing at the edge of a galaxy, gazing into its heart. The stars shimmer like diamonds, scattered across velvet, their light traveling millions of years to reach your eyes. But what holds this cosmic tapestry together? What keeps these stars from drifting apart into the void? The answer lies in the unseen, in the dark matter that weaves its way through the galaxy, binding it with an invisible gravitational embrace. It's a reminder that beauty often lies not just in what we see, but in what we cannot. The universe is a place of contrasts, light and darkness, chaos and order, the known and the unknown. Dark matter, though invisible, is the silent architect of this balance. It shapes the galaxies, guiding their formation and evolution, and yet it remains hidden, a shadowy presence that defies our attempts to fully understand it. This duality is what makes the cosmos so enchanting. It's a place where science and wonder meet, where every discovery raises new questions, and where the mysteries of the universe invite us to dream. Consider the spiral arms of a galaxy, stretching out like the petals of a cosmic flower. These arms are not just beautiful, they are dynamic, filled with stars being born and dying, with clouds of gas and dust swirling in intricate patterns. And at the center of it all, dark matter holds the galaxy together, its gravitational pull shaping the paths of stars and planets, ensuring that the galaxy remains a cohesive, living entity. It's a testament to the delicate balance that exists in the universe, a balance that allows beauty to flourish on a scale beyond comprehension. But the beauty of the cosmos is not just in its grand structures, it's also in the details. The faint glow of a distant nebula, the subtle shift of a star's light as it passes through a dark matter halo, the quiet hum of a galaxy spinning in the void. These are the moments that remind us of the universe's quiet elegance. They remind us that even in the vastness of space, there is a sense of harmony, a rhythm that connects everything, from the smallest particle to the largest galaxy. As we reflect on the role of dark matter in shaping the universe, we are reminded of the profound interconnectedness of all things. The galaxies we see, the stars that light our night sky, the planets that orbit them, all of it is part of a larger story, a story written in the language of gravity, light, and dark matter. And as we continue to explore this story, we are not just uncovering the secrets of the cosmos, we are also discovering new ways to appreciate its beauty, its complexity, and its endless capacity to inspire. So let us take a moment to simply marvel at the universe, to let its beauty wash over us and remind us of the wonders that lie beyond our world. For in the end, the cosmos is not just a place of science, it is a place of poetry, a place where the mysteries of dark matter and the brilliance of galaxies come together to create something truly extraordinary. And as we gaze into the night sky, we are reminded that we are part of this grand, beautiful, and ever-evolving story. As we bring our journey through the cosmos to a close, let's take a moment to reflect on the profound role dark matter plays in the grand tapestry of the universe. From the swirling arms of spiral galaxies to the dense clusters that dot the cosmic landscape, dark matter is the unseen force that shapes it all. It's the gravitational glue that holds galaxies together, the silent architect that guides their formation, and the mysterious presence that continues to challenge our understanding of the cosmos. We've explored how dark matter's invisible embrace influences the birth of stars, the structure of galaxies, and even the behavior of galaxy clusters. We've seen how it weaves the cosmic web, connecting galaxies across vast distances, and how it shapes the very fabric of the universe. Yet, for all we've learned, dark matter remains one of the greatest mysteries of modern science. Its elusive nature reminds us that there is still so much to discover, so many questions waiting to be answered, but perhaps that's what makes the universe so captivating. It's a place of endless wonder, where every discovery leads to new mysteries, and every answer sparks new questions. Dark matter, though invisible, is a reminder that the universe is far more complex and beautiful than we can imagine. It invites us to look beyond what we see, to explore the unseen, and to dream of the possibilities that lie hidden in the cosmos. So as we gaze up at the night sky, let's not just see the stars and galaxies, let's imagine the invisible threads of dark matter that bind them together. Let's marvel at the delicate balance that allows galaxies to form, stars to shine, and planets to orbit. And let's remember that we are part of this grand, interconnected story, a story that began billions of years ago and continues to unfold with every passing moment. The universe is a place of mystery, beauty, and endless discovery, and as we continue to explore its secrets, we are reminded that the journey is just as important as the destination. So dream of the cosmos, wonder at its mysteries, and let the beauty of the universe inspire you to look beyond the stars. After all, the night sky is not just a window to the universe. It's a mirror that reflects our own curiosity, creativity, and boundless imagination. Now, as we wrap up this cosmic journey, I'd love to hear your thoughts. What fascinates you most about dark matter and its role in shaping the universe? Do you have any questions or ideas about how galaxies form and evolve? Share your reflections in the comments below. I'm excited to hear your perspectives and continue this conversation with you. If you enjoyed this exploration of the cosmos and want to dive deeper into the mysteries of the universe, don't forget to subscribe to the channel. There are so many more cosmic sleep stories and fascinating topics waiting for you, from the birth of stars to the secrets of black holes. Hit that subscribe button and ring the notification bell so you never miss an adventure into the wonders of space. Thank you for joining me on this journey through the stars. Until next time, keep dreaming of the cosmos and let the mysteries of the universe inspire your imagination. Good night and sweet dreams. you.